Well, okay, so I'm going to turn around to talk about something quite different from my scientific exercise here. When I turned from engineering to biology, I thought for the rest of my career I would devote my life to research in biology. But it was kind of unexpected that there was a call to return to my engineering route. And that's due to the surprising discovery of the deficiency in the hearing aids, this call of duty, so to speak, in working and move into this direction. This happened about 15 years ago. So I want to talk about the hearing aids project. And first of all, I'd like to identify, to inform you of the problem that is faced by the hearing aids, and then our approach in designing the hearing aids and the strategy, and how we validate the concept, first through computer simulation and human tests, and secondly by designing the scientific prototype. And from that we evolve, then move on to consider the product prototype, and we have to address the issue of low power, low voltage, and computational efficiency, and then technology that is required to develop the real product. But really this is where we stop, because we license our technologies to a hearing manufacturer, and afterward then we are told not to consider any of this. But nonetheless, that we have to also have to consider then for the overall product, that we have to consider the designing of the intelligence in the device, because hearing aids is not just really one device, a simple device of sound amplification of the sound that we don't hear, but rather than actually needs to mimic what our ears tend to do in our everyday living condition. Okay. You may not be aware of the fact that when you are in the room, that you really quickly, immediately develop the assessment of the room characteristics, how reverberant is the room, and what is the size of the room, and you actually adjust your vocal production system in accordance to the physical acoustic properties of the room. You probably don't even know that you are doing that, but yet most of our devices don't have this device intelligence. We don't have the ability to assess room size, or the ability to properties, or analyze the complexity of the auditory scene. Talk about scenes because we'll quickly go through that. And then what about intelligent processing? So a lot of our thinking really comes from the biological root, in terms of really how we analyze them, how animals analyze them, and how they deal with the everyday problem of sound communication. So first, quickly then, to talk about the real-world environment, because this is really crucial in terms of our design concept. Because we want to have a device that can operate in real-world conditions. And that is really the shortcomings of most hearing aids. They perform well in isolated environment, but they don't perform well in real-world environment. The real situation in everyday living condition often contain multiple auditory objects. So I'm talking here, and somebody is making noise, either you moving or somebody else talking, and the sound originates from different physical locations, and they are very different, but sometimes also overlapping spectral and temporal characteristics, right? When you're at a party, at a picnic, etc., people are talking, and most of their speech masking is the real problem. And another complicating factor is that listening rooms are reverberant, and echoes usually increase the background noise and really make it difficult for you to localize sound, because sound seemingly emerges not from one location, but actually from multiple locations because of the reflection. and it confounds sound pattern recognition as well as sound localization. So we have to deal with those issues. So unlike the visual system, where the images of the visual world are actually mapped onto the photoreceptors, certain photoreceptors actually pick up the signals from different individuals here. The auditory system operates very differently. Think about this. All the sounds that you hear actually have to enter the ear canal and into the ear. And it is up to the auditory system. The auditory system in the brain must do the sorting to actually group the stream of sound associated with any one object and separate that sound from the other streams of sound associated with neighboring objects. So you have to perform this grouping and then the stream syndication. But this is a very complicated process that has to be done in the brain and not by the ear or the ear canal. And a listener can usually only focus on one or two objects. Some individuals are as good at picking up two objects at the same time. I'm not. I can only focus on one. And actually this information, when you think about it, actually you have to pay attention to really pick up the signal. So in a cocktail party, all right, you have, let's say, dozens of individuals, hundreds of individuals talking. You can only pay attention to one individual talker. And you can shift, though, from one moment to the next moment to pick up the different individuals. But any one time, you can only focus on one object, right? So keep that in mind. The information actually you actively acquire, and you only focus to one object. Okay. As we age, as Casey is saying, actually as we age, many of our hearing abilities decay. And if you consider that actually essentially neural hearing loss, SNHS, is actually the most prevalent neurological disorder. And with age-related hearing loss being the dominant, essentially neural hearing loss. Okay. So in terms of the prevalence of the diseases, this is second only to arthritis. It's just so prevalent. Currently in the US, there are about 35 to 40 million people that have hearing deficits. And of this, only about 10% to 12% of people actually have hearing aids. Well, due to a number of factors. One is the cost. It costs a minimum $1,500, and it ranges up to $6,000 to $7,000 per hearing aid. It's not covered by the insurance, and it has stigma because if Casey or I were hearing it, you can really tell that I'm probably 60 years old or older or something like that. I don't like to do it. So there are a number of problems. And the fact is, as we age, our ability to hear higher frequency sound is reduced. Not only our ability to pick up the sound is reduced, but our ability to process sound also is reduced simultaneously. Our ability to locate sound, localize sound, our ability to suppress the interfering sounds when there are interfering sounds, we tend to be less able to differentiate sounds and focus on any one sound. And our ability to detect the fast transition, the fast transition, because that is crucial in terms of speech processing, that is reduced. Our ability to detect temporal gaps in the speech, from one syllable to the next syllable, and those gaps are crucial in terms of speech processing, that is also reduced. And consequently, when we are older and hearing impaired, we have difficulty understanding speech, particularly in crowded environments with acoustics, classic. So the solution to hearing aids have been considered to be really quite effective. And they are actually designed to offsetting our ability, the lack of our ability to hear maybe is to hear versus improving the understanding. Okay? So if you don't hear sound, let's say in the 5 to 7 kilohertz range because of aging, because you're over accessing exposure to loud sound, loud music, wearing the iPhone, headphone all the time, and you're going to have this deficit eventually, sooner or later, maybe sooner because of the headphone effect. And hearing aids generally offer limited. The people wearing hearing aids often come in. I mean, this is a typical coming because we have done demo for multiple years. People always say, "Oh, I can hear you all right. There's no problem with hearing. I don't understand you." So when this problem was first presented to me, because I was serving on the NIH section as the chair of the section for 2 years, and then I was invited to be an active contributor to the long-range strategic plan of the National Institute for Deafness. The problem was first exposed to me that actually this is a severe problem. The acceptance rate of hearing aids is very low because people always complain, "I don't understand what I hear." So this is a very different kind of problem. And when I first heard about this, I really did not believe that. And I actually consulted my engineering colleague at the Beckman Institute. And he said, "No way, I mean, we can design any gadget." What do you mean with it? This is not effective. And after we consulted our colleagues in the speech and hearing department, and they tell us, actually, this is real true, that people always say that they don't understand what they hear. And so this is a very different kind of problem. So to provide some relief to this particular problem of not inability to understand, people have designed directional hearing aids by putting directional out to the microphone, and sometimes they even design this fixed or adaptive array by putting a array of microphone either on the chest, headband, or whatever. But most of the solutions are not very particularly effective or not practical. But they're good in actually separating sound in front of you versus those sounds in the back of you. But if you want to discern the sound from multiple sources in front of you, those are not good enough. Okay? The third problem with the hearing aids is really that actually, if you wear one, you have a problem. Your ear is kind of a non-linear device, right? When it's very intense, when the sound in the environment is very intense, you actually shut down the volume of the sound by contracting the middle ear muscle on the top in order to really protect your eardrum. You actually contract the middle ear muscle to attenuate the sound that's entering into the ear canal. And so actually it amplifies weak sound. It actually weakens the very intense sound. And hearing aids are designed the same way. They're non-linear. When the sound in the ambient is weak, it amplifies a lot. And also selectively in certain frequency band that you can hear. But when the sound is very intense in that ambient, it actually amplifies nothing at all. So when you are non-linear, when you have a non-linear system, that actually you have a problem because our ears are used to processing the signals that are transformed by our ear canal, and it actually has certain expectation. As I said, you have to group the information and then segregate information from one stream to the next stream. So when the device really, when the devices or the ears are not getting the expected input to perform this grouping and stream segregation, you are in trouble. Because then the sounds becoming non-coherent sound, because sound stray from different streams cannot converge to form this what we call coherent perception of sound. Okay, so we have a problem. When you have two independent aids, you have a problem. Or a single aid, that aid is not performing what the ear normally performs. So you cannot perform this coherent perception or unitary perception of sound outside. So what we decide to do then is really to develop hearing aids that really can improve the speech understanding rather than ability to hear. So we want hearing aids that can extract a speech signal in the presence of multiple competing sounds. And here is an illustration of the example. Let's say you have 3 talkers talking simultaneously in front of you. All right. What we want to do is that while the ear is picking up this combined signals speech cycle, what we want to do is selectively picking up the signal from only one of these. That's this guy in front of you, right? What we want is just the individual input rather than multiple. So I think the strategy in the biological system typically is involving this what we call localization first. When you locate, just like when we're doing the attentional hearing, you precisely say, I want to listen to that, either by doing the sound characteristics from that individual or by the location of that individual. Location is the simplest thing. Most individuals do that. We locate, and then we just focusing the sound only on that aspect and drop the rest. So this is, I think, the strategy we decide to do is that we localize and then extract the sound from that location. Rather than by picking up the sound characteristics and extract that sound. So you've heard about the ability, incredible ability of frogs to locate the sound. And so, I mean, this is from my dissertation work at Cornell. And I studied sound localization problem in frogs. And I learned very early on that frogs can locate sound quite well, but it requires input from both ears. If you block the input from one ear, let's say if you block the right ear, and there's going to be left with bias in localization. Sound. If you block the left ear, you have right with bias, and you can't locate the sound. And control no problem. So it really requires the 2 ears to process the signal. That's perfectly understandable. And then sound localization involves both ears in all animals that we know. But for frogs, it's kind of unique that actually the binaural processing occurs right away at the level of eardrum. It doesn't have to wait until the signal reaches the brain of most animals, mammals, and birds. That is because the air eustachian tubes are generally open. As I said in the previous example, in the first talk, I described that some frogs have the unusual ability to close down this eustachian tube. But almost for all other frogs that we know of, the eustachian tubes are permanently open. So sound coming from one ear, let's say the left ear here, will go to vibrate this and passing the pressure to the ear, the middle ear cavity and the mouth cavity. From there, it actually goes in. So the vibration of this eardrum on the right is actually subjected to the sound pressure from the outside as well as the internal pressure. So this kind of receiver is what we call push-pull receiver. Okay, push-pull. Push-pull receiver is very advantageous because it is directional sensitive. It is sensitive to sound direction. It makes the ear directionally sensitive. So the interaction, binaural interaction, occurs very early and then followed by the signal processing in the brain. So the push-pull receiver basically is a pressure difference receiver. The pressure from the outside is bigger than the inside. So actually the outside will, right? When two pressure equals, basically you have none. So actually it becomes very insensitive to sound coming from the straightforward direction. And this pressure difference receiver principle is what we use in our design. So when we design, then coming from the outset, that we want to actually design a system that extracts the signal and make the speech more understandable. So we decided then to utilize 2 microphones, either designing around the corner of the eyeglasses or in the microphones in the hearing aids, the 2 hearing aids. And we want to integrate the output to form a uniform output, a single unified output. And we are going to try first using very simple arithmetic operation. And that is equivalent to pressure difference receiver, because the push-pull receiver is basically subtraction algorithm and acoustic receiver. We want to try whether or not that is successful. And then we want to allow the listener to actually determine which target is the target of interest and let the individual regain the control of the active listener. Remember, when you wear hearing aids, you're strictly at the mercy of the device performance. And devices, as I said, removes your ability to actively listen. And we want that to be returned to the owner of the device. We want the listener to be able to actively steer the target signal. So we first tried the localization and extraction algorithm, and we really used the biological principle. We sort the signal. We first perform the frequency analysis, the Fourier transform, break down the sound frequency into individual Fourier components, F1 to Fn, doing it both the left microphone and the right microphone. And from there, we actually feed the signal into a dual delay line. This is a structure in the brain that we know of that actually accepts the input from 2. And we perform this very simple arithmetic to try to see whether that turns out to be the right solution for localization. And we talk about the stencil filter. Once we localize, then we want to do noise cancellation of unwanted signals, and then we want to do the frequency synthesis. So the dual delay line is the crucial structure here for identifying source location and for extracting the content of the signal at that location. Now we'll talk about the scheme of localization as well as the extraction. So let's go back to the biology again. From various evidence that we have seen, actually the brain actually has this unusual circuitry, okay? And this is called the dual delay line. So the output of the 2 ears, let's say this is not microphone, this is ear, left ear, right ear, okay? It's first transmitted to a structure called cochlear nucleus. From the cochlear nucleus, signals output is projected to another structure called superior auditory nucleus. And this output projection here is actually quite specific. That it actually sends the output from one neuron to multiple neurons within the next structure. And this actually neurons perform what we call coincident detection. So let me illustrate the process that's taking place here. Let's say there's a sound coming from straight ahead. Okay. So a signal from here is going to arrive at the 2 ears simultaneously at the same time. From here, signal is going to reach the teeth at the same time. And therefore, when this signal is now transmitted to the next station, this is going to traverse to somewhere in the middle of this dual delay line. Right? This short delay, longer delay, longer delay, longer delay. Here, short delay, longer delay. Reverse pattern, okay? Same time here, and therefore these two are going to coincide in the middle. So only these neurons will be excited to inform you that the sound direction is somewhere in the middle of the auditory space. What happened now if the sound is deviating from the midline and coming closer to the right ear? Okay, let's say this point. And this distance is shorter, and this is going to arrive, signal is going to arrive here earlier, and this distance is longer, signal is going to arrive here later. So now this signal is going to traverse longer along this delay line before it meets the signal. So now coincidence is going to take place in the neighboring cell, right? So if you move this further and further away to the right, the coincidence is going to take place further and further to the left and the way down. On the other hand, if the signal now deviates from midline to the left-hand side, the coincidence will take place further and further to the right. You get it? So what you have here is a translation of the space into delay, and then back, and this is a one-to-one map of the time delay, or the location now of this thing, of the coincidence, that tells you the actual location of the source. Okay. It turns out that this coincident reflection scheme can be described by simple signal extraction, by subtracting the signal left and right. Not only that gives you the precise location of where the sound is, but also it also gives you the ability to extract, to identify the content of the signal from that location. So mathematically, it turns out that the subtraction scheme works both to locate the sound as well as extract the signal from that location. As you know, in engineering, it always comes down to equation, but the equation gives you the right solution. So we were so fortunate in that regard, and utilizing the Frog's localization scheme, the subtraction scheme, to extract the signal as well as locate the sound. But there's a problem in terms of this scheme. So you divide the sound into the various order spectrum, low frequency all the way, let's say, to 6 kilohertz. But you see, with increasing frequency of the sound, the waveform period gets shorter and shorter, right? So whereas something at low frequency, there is no ambiguity due to the coincident protection. But as the frequency increases further, for every location, let's say the coincident pattern for sound at 0 degree, not only that you have this coincident here, but also you have the coincident also at the next point here, it is 1200, and the next one. That tells you also sound is also at 0 degree. So you have this ambiguity. At higher frequency, you have multiple ambiguity. Let's say at 3 kilohertz. This point, this point, this point, this point, and this point. Higher frequency, you have even more. Okay, so this is what we call the stencil pattern. This is for 0 degree. We actually can develop the stencil pattern for every single location. 5 degrees, 10 degrees, 11 degrees, 12 degrees, etc., right? So we actually, instead of letting the ambiguity patterns, because of the higher frequency, the shorter wavelength, to detract from localization speeds, we actually use this information to help us to extract the direction of information, to remove the ambiguity. So an illustration of this thing is actually shown in the next slide. So here is a sound for originating from 60 degree to the right. Okay, the coincident pattern, you extract this thing, and then there is this coincident pattern also, right, from higher frequency. So we're actually simulating the localization scheme here by using two topics at -60 and +45. So this would be the stencil filter, and you can see at 5 millisecond point, this is a speech sound, actual speech sound, that you have a very chaotic kind of coincident patterns. It doesn't tell you much of anything. But when you wait till 60 millisecond later, then you see the coincident pattern. Pretty much confirm this theoretical pattern. So when this matches, you say, aha, this sound actually comes from -60 degree. Okay, it tells you that actually this coincident is the real one. The rest you can ignore. Using the stencil filter then, you can actually determine the absolute direction of the sound precisely. What happens then when you have multiple sources? Let's say there are 4 talkers talking at 4 different locations, -75 degree, 0 degree, +20, +75 degree. And you have different words. One guy is saying armchair, playground, pancake, woodwork, and we can look at a different time, and you can see this emerging patterns coming in and out, in and out, in and out all the time. So actually the sound wave is complicated, but actually from the localization algorithm, you can actually identify the absolute locations of the 4 talkers. Here at 175, 0, 5, and 7. Actually, we can further take advantage of the fact that this signal is going in and out all the time, so we integrate all the time, and then over the frequency for picking a central pattern, central filter, then we can identify the location of the 4 sources. For instance, in this case, if you do thresholding, then we can one source here, one source there, one source there, one source there. So it's very powerful technique for us to. So once we locate the sound sources, then we need to then process the signal. We want a clean signal. We don't want a slider signal because we want a clean signal to stimulate the brain to inform us of the content of the signal in that sound source. So then we have to do the noise cancellation. For noise cancellation, that we left the algorithm to figure out for us. That one instant, which is the one that actually interferes the signal processing the most, other than the signal at the source. So we identify the louder sound and we cancel that sound source. So at one instant, we may be canceling the source from source A. At the other instant, we cancel the source B, source C, and etc. But at all the time, we keep the gain at 0. So, but the problem is this computation is challenging because you have almost limitless ability to process the signal. And we say, okay, does this scheme actually work? So we have to validate the simulation data. Not only it can extract the sound direction, but also actually improve the intelligibility of the speech sound. So we tested then with listeners, with normal hearing, as well as listeners with essentially neural hearing loss, and we use target stimuli from the data set developed about built-in speech and hearing. This is high context sound, then we have the competing sound, either 1 or 2, recording of multi-talker babble, maybe sound that's a combined sound of 12 talkers, and we present it at one single angle at different signal to noise ratio. I'm not going to go through this because this is really the preliminary stage that we decided that the intelligibility rating was significantly higher for processed entities than for unprocessed entities. So that encourages us that okay, it's time for us to build a real scientific prototype. And then at that time, we were using a personal computer that we quickly recognized the limitation of this complex algorithm and complex system design, that we probably have access ability. Because in the real world, when you think about it, when you are there in the room, listening to one talker, next talker, etc., you don't necessarily process the information. You try to localize every single source, every single location, but rather you're actually focusing on just one talker, locating that sound, extracting that sound only. We don't have the animals, us. We don't have this computation efficiency to process all of the information. And instead, our efficiency is limited to processing one sound at a time. So we thought there was an overkill in the system by doing that kind of heavy computation. So we decided that we couldn't do the real-time processing using the localization extraction algorithm. It just takes too long, a few 100 milliseconds, which is way too long for processing in video. We can limit it to about 10 milliseconds or less. So we then developed this minimum variable strategy. It takes the advantage of its computational efficiency. So then let me describe the second algorithm that we developed. This is called a frequency domain minimum variance algorithm. So we do as we did in the previous algorithm. We separate the signal by frequency. Then all we have to do is that we're just going to minimize overall strength constraint. So this is why this is called minimum variance, because we're basically minimizing the output energy of the signal. It's very simple, optimal processing. Just waiting, and then we just reduce the output signal and energy of the output signal. But with the constraint that we have unity gain, maintain the gain at one angle. So again, let's go back to the biology. Okay. We can focus on sound coming from any angle. At any one time, only one sound. So we can focus on 0 degree and 20 degree. But for people who are hearing impaired, what do they do when they can't understand what they hear? Remember I said in the first talk, animals can communicate visually or auditorily. And in fact, most people with hearing deficits, they actually use their eyes to look at the lip reading, to do the lip reading, using the lip reading to assist them to hear. So for them, because they're so accustomed to hearing deficit, the 0 degree becomes a target. So I think for the ease of the hearing aid user to use new type of hearing, we decided we just going to make it simple at the beginning. We're just going to assume that eyesight at the 0 degree, that will be the target signal, and we're just going to keep this gain at the 0 degree, 1, and then we're going to minimize all axis sound. Remember, when you minimize the energy of output signal with this constraint, basically the end result is minimizing all the off-axis signal, right? So that's really the scheme. And what happens? And this turns out to be quite encouraging, because we can determine using computer simulation that actually we have target signal at 0 degree, let's say, is producing the sound. All training was powered by steam. And you can have 12 talker babble that is 20, 30 dB more intense than this in technique. In theory, this should be masking everything of the combined signal of this set. So it's dominated by the talker babble, by the process waveform. You can recover the signal completely. Now, when you have 2 jammers or 4 jammers, let's say here, there's a jammer at 65 degrees, another jammer at 22 degrees. This jammer is, again, more intense than the signal, the target signal is 0 degree. The combined waveform is dictated by this 2. But then once we process, we can be able to recover a lot of the signal of interest, namely the target signal. So, encouraged by the fact that we can do this recovery of the signal of the target of interest, then it took us 2 years to actually develop this real-time prototype based on a TI chip, digital signal processing chip. At that time, it was very slow, at 133 megahertz. And we used various parameters, 256 point FFT, 8 kilohertz sampling rate, 16-bit frequency resolution. That's it. Okay. And so we now have to perform several tests to really see whether the real-time system works at all. So the input really are really 2 signals separately, right? So we call that cut 2 signals. If it's unprocessed, then you can feed the output of 1 microphone to 1 ear, 1 headphone, the other one to the other headphone. There will be the unprocessed signal. We can see whether or not the ear can process the signal well. And the final scheme is this one, all right? It's actually the conic. The data is processed. So there are 2 inputs, and then we do the FMD, and then we feed the same output, single output to both ears. So you have single output to both ears. Okay. So we need something intermediate here to really do second control, namely what we call the dialectic AMP process. We just sum the two and feed to one. Single output, feed to two. So we have three testing conditions here. Okay. One is the experimental, the other one two controls. So we want to examine whether or not the system works in real environment, real world situation. We're going to measure the signal reception, speech reception threshold in quiet and noise conditions with various different words and with different sentences. And then we're going to rate subject intelligibility of the sentence. And we tested subject with normal hearing, so subject with sensory neural hearing loss. And we're going to use different kind of jammers. In the first condition, we're going to use the reverse speech, meaning the speech playing back reverse in time. Use that as a jammer because that's unintelligible, right? So the first testing condition is really what we call the Thanksgiving dinner party, right? Thanksgiving, you're at a table, and you're talking to people in front of you. Let's say there are 5 individuals here, and you're trying to listen to this 780 SPL. And the other are talking also maybe to their counterparts across the table. Okay? They're all talking, and they're all talking at about the same level, and therefore this is a very difficult situation for us to listen to. Right? Let's see what they. So this is our ability to hear without processing. This condition actually, we'll see how easy it is for us to hear. Remember now we're using actually a directional microphone picking up sound in front only. This is already helpful. I got to do this. See how difficult it is? You can pick up maybe occasionally one word or the other, but not. On the other hand, once it is processed, it is so easy to understand. Okay, when you just play it again. It's difficult, but once it's processed, okay, so how much elevated is the signal, and the competing sounds are totally suppressed. So you can see that actually most subjects with SNHL will actually make the signal 50% more intelligible than that kind of unprocessed signal. The intermediate condition is kind of interesting. It helps a little bit, but not as much as the processing. So this intelligence really differs by 50%. So when you look at the speech reception threshold, again here, the lower the better. The direct process signal, you have lower threshold, lower signal level, and by comparison to unprocessed, you have to have higher signal level. So it's 8 and 11 dB better. So this is really the inexperience in our part when we licensed our technology, that we did not recognize that how much of this improvement, how valuable it is. Because I've heard subsequently, after we licensed our technology, that they say every 1 dB probably is worth at least $1 to $2 million, and yet we didn't take advantage of this. And we have tremendous gain in the signal. Now, not only people who are hard of hearing that are being helped, but you and I actually are also being helped. This is also interesting for people with normal hearing, that we can see that there is also significant gain for us. And actually, when we do the demo, we put the microphones actually on the corners of the eyeglasses. We actually have people in the room all talk at the same time. And there could be 8, 10 people or more people than that. And the fact is you can steer the thing and then pick up the signal and run. Time when we were doing this demonstration to in the company, we happened to have the reception party for the farewell reception for Larry Smart, who was the director of the NCSA, and there were about 200 people also at the Beckman Institute, but known that the wall is highly reverberant. So here in the company, the representative, CFO and CTO, came. They want to prove that not only work in our testing room, where we have the anechoic foam to remove the echo, but then force us to take the system down on a card and computer mount the echo to Rotunda. Rotunda at Beckman Institute is really a circular arena with echoes coming from all over the world. We've never tested that. Fortunately, our device was never up. They were convinced, at that point, they were already ready to license our technology. And then they saw this reception at the Beckman Institute. They said, well, let's try it. I said, well, there's no way that this device is ever going to work when you have 200 people talking at the same time. But I said, well, we know, just go ahead and test it. So we bravely just took our card to the agent of the Beckman Institute, and I gingerly accosted people in the reception and said, sorry, I disturbed you. And I was standing at the end of the party, and I started talking, and then the CTO said, I didn't hear you. I mean, they were just so at that point in time. And so I think, as you can see, we have done a lot of testing, scientific testing, with different scene, with different jammers. This time we used the speech-shaped cafeteria noise, which is also a very powerful jammer, and different passages, different sentences, and listeners, normal hearing, or listeners with essentially neural hearing loss. This time we create a situation whereby next to the target sound, you have a signal that is very strong, stronger than the target signal. And this condition typically is hopeless. And this thing is not stronger than this. And usually that will become problematic. And then the secondary jammer here also combined to produce overall signal to noise ratio of 40 dB. So this is kind of like the joyful picnic or the picnic that you're having here. Chopped into a video and some jammer coming out. Other people in the surrounding. Again, when you look at the percent correct, it's quite good here. About what, 40% difference. And that's really useful. And then you measure the speech perception threshold again. When you process signal, threshold is lower and threshold is higher than process. So we've done a lot of testing to really convince us that actually the FMD algorithm works almost in real time with a delay of about 10 to 15 milliseconds. It confers benefits across different situations, different tasks, and different computing signal types, cafeteria noise, reverse speech, or multifocal babble, and the response test, you have one metric, intelligent reading, or speech recognition, or speech reception threshold, and all conditions work. So then we need to start considering the product concept. Initially, we thought, we could put the microphones here in front, at the corner of the eyeglasses. But certainly this is not practical because nobody's going to wear a microphone here in the corner of the eyeglasses. So more practically would be putting the microphone in the ear itself, up here. This is behind the ear here. And so for that, you have to do some transformation of the signal so that this signal is representing sound from the side. And the further research work, as I said, we have to combine the signals from two microphones. And clearly, the ideal way is to produce interconnect technology using the wireless. So we have to allocate a team of students and postdocs to develop this wireless interconnect technology. And we have developed that. And then we realized that actually the listening conditions vary from time to time in different room sizes. So we need to have a way to analyze the auditory scenes for automatic selection of signal processing algorithm. So really, when you are talking to somebody in a quiet room, that you don't want to have this signal processing scheme, because I think simple amplification would do. But when you're talking in a complex environment with multiple talkers talking at the same time, that you need to activate certain algorithms. And so we decided then to pursue to look at the way to analyze the room reverberation as well as analyze this analysis of room sizes. I won't go through the detail because there are papers to describe this. But we actually used the optimization method to first roughly estimate the room volume. And then we calculate the error, minimize the error between true and estimated value, and then define the global minimum of the error to obtain the estimate of the room geometry. As you can see, this is true dimension of one room, for instance, and then our estimation comes up with something that's within about 10% or so. It's very good. And the second project involving the assessment of the room reverberation estimation, as I said, that actually most of us aren't aware that we do this automatically without knowing it. And then we developed this blind estimation of the room reverberation quality, measuring this reverberation time at 60 milliseconds. We used this MLE, maximum likelihood estimation algorithm. We came up with this blind estimation technique that we can actually assess the reverberation characteristics of the room automatically, because I think this is the true, actually there's bigger error here than other points. And so this has been very powerful, and we have the patent also for this technique. And the bottom line is really the work cannot be done involving multiple individuals. This is strictly teamwork. We have a team that is devoted to signal processing, this is the biggest group, and then some devoted to wireless communication, some to speech perception tests, and some to auditory system analysis. And we have really developed patents in all of this area, and altogether we have about 10 patents or so. And the support has come from the Beckman Institute, because we knew that we developing something totally new. We didn't have the recognition of being the experts in this area, and we have to develop teamwork to tackle these things. And so as you can see from this talk and the previous talk, that we see the power of teamwork. And that's really the note of future research, that one person was most likely not able to solve a lot of the problems. The engineering problems are defined, and sometimes it just happens in this case, as in many other cases, that the biological system can shed light in terms of how that problem can be solved. Because I think had we not known the biology of hearing and how we hear and how animals hear, then we might not be able to check the problems. The biological system has evolved over millions of years, and that's powerful because I think unless they evolve successfully, they're not going to be able to survive. And sometimes, I think, in the recent decades, anyway, the biomimetic approach has been found to be a very useful avenue in solving a lot of engineering problems. So the reverse engineering talk that I'm giving here illustrates that. So it's just going to make we think there's incredible synergism between the basic and applied research. Because from the applied research, we also all of a sudden identify many questions that have not been addressed in basic research. So we think really it's a really two-way traffic. I thank you.